Now to wrap up on Laplace transforms, let's look at an application, and this application is one in sort of mechanical control. It's called the inverted pendulum, and it's a very common example that people look at in signals and systems. But hopefully it should convince you also that these theory that we're learning and this sort of way of analyzing systems that we're learning is actually quite practical in the sense that it lets you analyze and design control strategies for real-world systems. So we'd like to be able to understand how to model a physical system as an LTI system. You may have had a little bit of experience with this before in physics or in differential equations. But then we'd like to be able to apply feedback control to stabilize this this real-world system, under the approximations that we use in the model. Okay, so what's the inverted pendulum? It's pretty straightforward. There's a little truck. It's got wheels, and we're thinking of it moving in a 2D, moving in a 1D line. It's a 2D problem because we're considering this mass m, which is at the end of a stick or a rod of length L, and here we have a hinge. I guess there's a hinge over here that allows the rod to rotate back and forth, and so we call theta of t the angle that it makes with this vertical line, and x of t is the position of the cart. So we want to be able to essentially move the cart back and forth, jiggle the cart back and forth, in order to keep the mass m vertical. And if you want to see some videos of this happening, you can just look on YouTube for inverted pendulum, and you should see some nice demos with actual robot carts that kind of keep this mass vertical. So what's the physical setup, right? The physical setup is this diagram here, and we have to make a couple of assumptions if we're going to try to analyze it. And we can relax these assumptions at the expense of a slightly more complicated model. And then some assumptions we can't really relax, otherwise we make the model, the system kind of unanalyzable. So we're going to act like physicists and just say, oh well, okay, the cart and the rod have no mass, so the mass is all centered on this ball here, and the connector, this hinge that's over here, this is frictionless, so this thing can swing back and forth easily. There's no drag on it. And the cart's motion of the cart on the ground is also frictionless. You can also reformulate this where you take x of t to be a force, and you put a mass on the cart. And that makes the problem a little bit more complicated. But let's try and deal with the simpler one for now. So x of t is the position of the cart. Theta of t is what we call the angular displacement of the rod, and this L is the length of the rod. And this length is actually important. It's not a throwaway parameter, because it's going to affect the torque. The longer the rod is, the sort of different moment of inertia from this from this mass sitting over here at the end of this rod. Okay, so we have to look at the different torques that are acting on this mass. Okay, so what are the different torques? Well, the line, if we have this sort of have to look at the horizontal line between the vertical of the cart to the rod. So that's using SOHCAHTOA. That's L sine theta. So it's the rod hypotenuse times sine theta will give you this horizontal distance. And then there's G, the force of gravity pulling downward on the mass m. So the torque is actually m times L sine theta times G. And so this is essentially all due to gravity. This is what's pulling the mass down to the Earth. And G, of course, is the gravitational constant. Then we have the action of the cart. So if I shift the cart to the right, the pendulum is going to try to swing to the left, or I'm putting a torque on it to make it swing to the left. And that is going to be given by m times L cosine of theta times the acceleration, that's going to, so m times this acceleration is the force essentially I'm applying to the cart, times this distance L cosine theta, and so that is a negative torque that's being applied to the arm of the cart. I mean of the arm with the ball on it, mass m on it. And then finally, the expression in terms of theta for the actual torque experienced by the thing is of course going to be the difference or the sum of these two torques that I have in the first two bullets. But what is that actually equal to in terms of theta? So we have a moment of inertia ml squared of the mass on the rod, and then it's going to be the second derivative of the angular acceleration. So that gives us this other torque, and we have to balance these three torques. So this is like a law of conservation of torque, right? We have to set the angular acceleration equal to the sum of the two torques. So basically you get this expression here. And this is super nonlinear because this sine function is nonlinear, this cosine function is nonlinear, so we have no hope to actually analyze this in its current form as a LCCDE, as a linear constant coefficient differential equation. So to analyze that, we're going to have to make some more assumptions. So this assumption is similar to ones that we make all the time when we talk about distances and angles. So one thing to think about is if the angular displacement is too large, there's no way we're going to be able to like swing it back up to normal. So we should really only think about doing this control for small values of theta. And for small values of theta, we can approximate sine theta and cosine theta. We can approximate them with a Taylor series, in which case sine theta becomes theta and cosine theta becomes 1. So we have sine theta is theta and cosine theta is 1. So this is a linearization of the functions or the system. Right, because now I can replace that cosine with just 1 and that sine with theta, and suddenly I'll have an LCCDE. And this, of course, will only happen if theta of t, which is much smaller than 1, or is very small, will these approximations hold. So we have to make sure that we're kind of operating in that regime, and this is a good example of applying linear system theory to real-world systems. It might be that there's only a certain regime of parameters in which the system really behaves linearly. Otherwise, all bets are off. And so your LTI system assumption is contingent on those conditions that you're operating kind of in the linear regime. And so a lot of circuits, for example, will have a linear operating regime, and then we'll do something weird and nonlinear outside that regime. So as long as you're operating within the range of values, like range of input values that for which this chip acts linearly, then you can treat it as a linear object. Okay, so this simplifies our differential equation. We have this original differential equation from the torques. Now I replace the cosine with 1, so I get this, and I replace the sine with theta, so I get this. Then we can divide by ml squared everywhere, and we can get this simpler differential equation. Over here, this is a linear constant coefficient differential equation with theta as the output and x as the input. So we can write the plant, right? So this is the plant, and the open loop system. This open loop system is minus s squared over L over s squared minus g over L, right? So this is just from doing this, from taking the Laplace transform of this differential equation. So far, it's now what we've done is, just to recap, we took this physical system, which was simplified in the sort of physics style of things by making some things massless and so on, and then we linearized it by operating in the regime where the angular displacement theta is not too big, and then we got an LTI system which we can whose Laplace transform we can write, and this is just the open loop system. So this is just the plant, and we can see here immediately that it's unstable. Right, so the transfer function is given here. If we cross multiply top and bottom by L, we get, s squared over L s squared minus G. The poles are at plus minus square root of G over L. And since this physical system is causal, right? We can't operate non-causally on this cart. The ROC is going to be to the right of the rightmost pole, and that's the rightmost pole is positive. It doesn't contain the imaginary axis, so this system is unstable. Now, of course, you look at it, the physical system, and you're like, obviously this thing is unstable, but like mathematically, it's also unstable. So that's a good looking at reality is a good sanity check on your math. So what can we do now? We have this g of s, so we can compute the output of the system with different inputs x of t, and maybe some of them won't make it blow up, but in fact, pretty much anything you put in is going to make the output blow up. And so then the question is, okay, how can we use feedback to control the system? Now, it's not clear that you can immediately apply feedback, because in order to apply the feedback, you need to be able to detect the angular displacement theta. So we need something that can measure theta of t, like a little sensor, for example, on the hinge. That could be on the hinge, or it could be a camera that's looking at the system and then estimating using computer vision or something, estimating the angle between the rod and the vertical line. But we need some kind of sensor in order to measure theta of t, and then if we have that sensor, we can use the feedback. We can use feedback to stabilize the system. So the plant, remember, is this minus s squared over L over s squared minus G over L. So if we want to use closed loop feedback control in the same way that we looked at before, we can try to stabilize the system. And for this system, we're going to try proportional integral control. And why are we going to do that? Because it turns out that P control and PD control both don't work. That is, you can't stabilize the system using P control and PD control. And I recommend try to show P and PD control don't work. I think that's a little good exercise. Maybe you can do that after we go through this derivation here. So our feedback control is Kp plus Ki over S, and then we have for the closed loop system, just plugging things in, we have this Kp plus Kis, that's f of s, times g of s, and g of s on top. And so we have to do some algebra to simplify this. So again, we have this closed loop system, multiply top and bottom by L s squared minus G, and we get the final closed loop system is minus s squared over L minus Kp minus Kis minus G. All right, so this is this is a bit complicated now. We have two parameters, Kp and Ki, and so we can potentially move the poles to all sorts of different locations in the closed loop system. But if we want to get what we want is to get a stable system. So in order to stabilize this, maybe we want to make all the signs in the denominator positive or all negative, since it's a negative in the numerator. So let's set Kp equal to L plus alpha. Then we're just going to get an alpha over here, and the negative signs will all cancel. So we get s squared over alpha s squared plus Kis plus G. So now we just have one parameter. I mean, we have alpha, but we can solve for like Ki and the relationship between Ki and alpha a little bit more easily. So let's look at this closed loop transfer function. Right, this is the closed loop system. Then we can analyze this, of course, using the quadratic formula. We get minus Ki squared plus minus square root Ki squared minus 4 times alpha times G, all over 2 alpha. And we can see where these move numerically. So we could plot this out. We can actually plot trajectories. Trajectories correspond to something called the root locus method. where you actually kind of look to see where the poles move as you tune, say, ki for a fixed alpha. And this is kind of like, and it looks a little bit like a football diagram, where you see, certain players are moving. You have a little X, and it has an arrow to where it's going to move. Similarly, you have this sort of thing in the root locus plot. And this is a topic for the control systems class. But if we want to just sort of explore it in a little bit more hands-on ad hoc kind of way, we can try to consider this what we call the critically damped case, where the poles are identical. And if you want the poles to be identical, you need to have the discriminant here. This discriminant has to be equal to 0. So that means ki squared is 4 alpha g. And so if we take alpha to be 0.5, then we can set ki to be square root of 2g. That's square root of 20 or so. And then we'll get the poles in the same location. So let's look back and see how we did this. How do we apply Laplace transforms to a real world system that we'd like to analyze and control? So first step is usually to use physics or whatever the domain expertise is of this problem. Often it's physics, but sometimes it might be chemistry, it might be biology. You want to use those rules that explain the relationship between the input signals and the output signals. And those relationships might be complicated and nonlinear. But you want to write down some sort of differential equation that describes the relationship between these signals. And then the next step is to try and figure out a linear regime, a regime in which you can assume that safely assume that all the relationships turn out to be a linear constant coefficient differential equation. And so this involves figuring out, what is the operating regime of the system. In this case, we said this system will work as long as theta is small. So let's make the assumption that theta is going to stay small, in which case this linear system is going to work. Then you have to then go through our regular Laplace transform analysis steps that we've been doing over and over. You generate the Laplace transform for the open loop system. We close the loop by applying feedback control, and then find parameters which can stabilize the closed loop system. And if you want to do some more after that, you can, plot these pole zero diagrams. You can plot the impulse response. You can plot the frequency response. You can see try to characterize the behavior of the closed loop system using the other tools that we've developed along the way to understand Laplace transforms. And so I hope this sort of shows that all of the things that we've been looking at have been building up to being able to now take real-world systems and analyze them and put them in the framework of the mathematics that we've been learning. And it's important to have that framework because it means that we can start looking at similarities between different systems. This physical system might be similar to a biological system, or it might be similar to a chemical system, or it might be similar to a different type of physical system, in the sense that the same differential equation is governing the responses, so the same feedback strategy should work. So if you go through these steps in another problem, you can, for example, find examples in textbooks like the Ullaby and Jägel textbook, which will give you an example of how to apply this for other problems. Okay, so if you have some more questions and a little bit more try it yourself, you can write down a lot of different physical systems. You can write them down using RLC circuits. You can write them as spring mass damper mechanical systems. And all of these systems, these simple systems, will lead to linear constant coefficient differential equations, which you can then analyze and apply feedback for stabilizing the system. So that's like a shorter step. If you start with an RLC circuit that produces an unstable output, you can analyze it sort of more directly, just using Laplace transforms, without having to do all this linearization stuff. So as I said before, you can try proportional and PD control on this inverted pendulum and see essentially that it's not enough to control the system. But maybe you can try PID control. So maybe you can try all three, proportional integral and derivative control. So what would that look like? That would look like saying f of s is equal to kp plus kds plus ki1 over s, and then see how this might change how you move the poles and zeros around. So this you might want to explore numerically using MATLAB, and then try to see, does this added derivative control actually help you stabilize the system much at all? And I actually don't quite know the answer to this off the top of my head now, but you can try to make a case that it helps or it doesn't help. Just proportional and derivative control doesn't seem to help. So it is adding it with the integral control. Does it make somehow this system a bit easier to design, or give you some more flexibility that you can take advantage of? So that wraps up our discussion on Laplace transforms. And the next topic we're going to move on to is Z transforms, which are the analog of Laplace transforms for discrete time signals in discrete time systems.